Well, let's talk about chaos engineering. So starting with what do we actually mean by chaos engineering? Because I'm sure by now you probably heard about Netflix doing chaos engineering, Amazon doing chaos engineering, and pretty much everybody else, all the big guys are doing that. But what exactly are they doing exactly? So I went to principlesofchaos.org and actually found a nice quote here that says, chaos engineering is the discipline of experimenting on a distributed system in order to build confidence of the system's capability to withstand turbulent conditions in production. It sounds great, except it's very vague in terms of what do you actually do. So what I like to do instead is think about analogies to things that we all understand. In this case, in terms of vaccinations, and in the case of smallpox, which was easily one of the most deadly diseases that we've ever encountered as a species. And it was killing people by the hundreds of thousands every year in Europe alone, until about 1798 when Edward Jenner first developed the first vaccine. And he actually got the idea from hearing, after he heard some stories of, I think, villagers in China, where they were counteracting smallpox by inhaling small amounts of smallpox material through the nose. So he developed the idea of vaccination, of how you can develop vaccines to basically to do the same thing on a more global scale. And 200 years later, we were able to eradicate smallpox on a global scale, and that's quite a big human achievement. And today, we have over 25 different vaccinations for different infectious diseases. And in the UK, by the time you're 14, I think you get about 20 different vaccinations already. So vaccinations has become our most effective defense against those infectious diseases. And I'm sure everyone here understands how it works on a simple level in terms of it stimulates your body's immune system to recognize the foreign bodies as and start to build defense against them before you actually come into full contact with the disease itself. And you do this by injecting the body with a very small sample of the disease that you're trying to protect yourself against. And that's where I found we can find a lot of parallels between vaccination with the practices that we employ to do chaos engineering, whereby we are using experiments that are designed to trigger some failure modes in your system so that we can learn about how the system fails under those conditions in time before it actually happens in production, so that we have a chance to learn about system's behavior under failure modes and then build defense against those failure modes before it happens in an uncontrolled manner in production. So it's fair to say that chaos engineering is the vaccine to frailties that we have in modern software, which is full of microservices, many dependencies. In fact, if you've seen the sort of service graphs that Amazon and everyone else has published, what they call microservice Death Stars, where there's so many different connections, it's very difficult to understand exactly what is happening and how your system is going to fail. So my name is Yan Cui. I'm a principal engineer at a company called The Zone. And since I think July this year, I'm also one of the community heroes for AWS for my contributions in the serverless space. So The Zone is a sports streaming platform. So you can think of us as Netflix in that we have the same pay or monthly flat fee model, where instead of streaming movies, you can stream live sporting events instead. We support over 40 different sports and 200 different leagues around the world. And recently we started streaming in Serie A and B in Italy, as well as boxing matches in the US. All in all, we are available in 7 different countries and over 30 different devices. And at peak, we have just around 1 million concurrent viewers on our platform for one of the sporting events. And we are based in London mostly, but we also have offices in Leeds, Katowice in Poland, as well as in Amsterdam. And we are hiring across the board for different roles in all the different locations as well. So if you're interested in working for us, then come talk to me or my friend Thomas there, who you can recognize the Zone logo. I want to start by talking about a pretty significant problem that we have with chaos engineering, is that it's got this image problem. I keep reading blog posts on the line with titles like Breaking Things on Purpose, or meetups with titles like The Joy of Destruction, which for me just puts way too much emphasis on the act of breaking things, which is not what we actually want to end up with. We don't want to end up with a broken system, in the same way that when we apply vaccinations to patients, we are not hoping that they will catch a disease. It's quite the opposite, right? And if you conflate the action of what you do with that payback, then it's quite easy to misunderstand why we're doing things. In the same way that if you have a constructive argument with your colleagues about how to approach a particular problem, the argument itself is not the point. You're trying to come up with the best solution together, and the argument is just how we get there. And instead, often when I talk to people about what you're doing, how you're approaching chaos engineering, or are you thinking about it, I almost find this what do you call it, a cavalier attitude towards breaking things in production, as if it's just a cool thing to do, is what the cool kids are doing. I can't stress enough that the point of doing chaos engineering is not to break things. It's quite the opposite. It's about building confidence in what your system is doing by repeatedly running experiments to understand how your system actually behaves under failure conditions, so that you have time to build defense and put in the engineering effort to make things better, so that when they do happen, when those failure conditions does happen in production, your system is going to be fine. The point is not to break things in production for the fun of it. And when you do want to think about, okay, what do I actually need to do in order to apply principles of chaos engineering to my organization? If you go to principlesofchaos.org, it's got a great website, and it outlines 4 simple steps that anyone can follow. Step 1, you have to define what normal looks like for your system. And if everything's on fire all the time, then, well, you're not ready to do chaos engineering because you don't have a steady state. You don't know what normal looks like because normal doesn't exist. In the same way that you wouldn't give someone a vaccination if you know their immune system is already shot to bits, and even a small sample of disease is going to hurt them, it's going to do them more harm than good. So you wouldn't want to start doing chaos engineering and start breaking things on purpose when you don't even know what normal looks like. Once you know what normal looks like for your system, then you can start to hypothesize different failure scenarios and how your system would behave or perhaps should behave. And then you can start to run those experiments. Doesn't have to start in the production. You can start in fact, you should start in an environment away from production where the stake is not so high, in case there are some things you didn't understand your system will behave in a certain way. You should definitely explore scenarios where you have just no idea what else is going to happen. If you're, say, building you've got a data processing system, what happens when your, say, DynamoDB or S3 bucket S3 start to fail? You probably don't. Well, chances are you probably don't know exactly how your system is going to behave. It's important to experiment with those scenarios to see how your systems behave, so that you can understand how you can then to improve things. But because those scenarios, you have no idea what's going to happen, you have no confidence in your systems in doing the right thing, so start those experiments in an environment outside of production. There's a lot of learning to be done in an environment like staging, where you have a production-like setup, where when you do get things wrong, you're not going to cause a proper outage in production. And any experiment that graduates into production needs to be carefully considered and carefully planned. You should have very good level of confidence that your system is going to do the right thing, because we've done this in staging, we've tested it multiple times, we've found the problems, we've put in the engineering effort to make things better, so we know pretty sure that things are going to be fine. Then you can start to graduate those experiments into production. That's where you run the ultimate test to know that, okay, if this does happen in production, we are going to be fine. Because again, the goal is not to actually end up with a broken system in production. And if you know something's going to break, you know your system's not going to be able to handle certain type of failures, and you did it anyway, then for starters, you haven't learned anything you didn't know before you go into production in the first place, and you're just being irresponsible. You're breaking the system, you're hurting your users' experience, and you're not learning anything in the process. That's not chaos engineering. That's not a chaos experiment. All you're going to do is piss off your users and end up with loads of complaints to your customer support team. And next step would be, how do we then actually to inject failures into the system? And this is where tools such as Netflix, CMan Army comes into play. And the Netflix also published a very nice book you can download for free from the O'Reilly website that talks not just about the technical side of things, how they execute those experiments, but also the social side of things. How do you communicate to other teams what you're doing? How do you plan and execute? How do you run game days so that everyone can get together, do brainstorming about how the system can fail, what sort of failure scenarios we should experiment with. And In terms of tooling, you can also find the Gremlin. This guy's very worth checking out. They build a tool essentially for you to execute many common forms of chaos experiments yourself with a lot of tooling for automation as well as scheduling, so that people can see what experiments are planned, doing at what time, against what environment. And whilst you're running experiment, you are collecting metrics from your system, and then after the experiment, you then go through those metrics to see whether or not you can prove or disprove your original hypothesis in terms of how your system would behave. And if you were able to find evidence that your steady state was impacted, maybe it's your number of requests that were completed that returns with a 200 response code, for example, then now you found the weaknesses, and now you have time to then actually start to build defense against those failure modes. And since the point is not to actually hurt production, and that we just want to learn about things and to make things better before they actually happen in production, we need to make sure that those experiments that we're running are under control so that we can use them to build confidence in the system, which means containment and the blast radius should be front and center of your thinking at all times. And the number one thing you need to do is make sure that whatever it is you're doing is well communicated to everybody involved. In a large organization, the chances are many teams are going to have their own services. You're going to have to communicate with other teams what you're doing, especially if what you're doing is going to impact your downstream teams as well. It should never be the case that I'm coming to the office one day and realize all my dashboards are red, and by the time I dig into it, I found out that someone else from a different team is running an experiment, and things just happen unintentionally, start to break all my system as well. It should never be a surprise to anyone else that can be impacted, that what you're doing when you're running an experiment. Another thing to keep in mind is in terms of timing. You definitely want to run experiments during office hours when people are in the office and in front of a computer, so that if anything that goes wrong that you didn't plan for, at least they're in the office, they can deal with it. And if you have important dates coming up, in the case of Netflix, if a new season of Daredevil is going to launch soon, or in the case of The Zone, if a big boxing match is about to happen, or Real Madrid is about to play Barcelona, you don't want to go anywhere near your production system with your fancy chaos experiment and unintentionally break things when such important events are happening. There's a time for taking risks for the sake of learning, but then there's also time for just, for good old common sense and just not take any unnecessary risk when you don't need to. In terms of containment and the blast radius, you want to, and this is especially important when you start to graduate those experiments into production. It's important, again, remember, we are not looking to actually break production. You want to make sure that you do the smallest change possible that still gives you the ability to pick up signals, whether or not your steady state was impacted. So in the case of, say, using Chaos Monkey, you want to terminate one server at a time, or in fact, one small percentage of requests at a time, as opposed to knocking down the entire cluster. And you should always have a rollback plan ready at hand as well, in case anything unplanned for started to happen. You start to see behaviors that you didn't think possible, or you didn't see when you run the experiments in staging environment. Then put a stop to it right away, and then roll back whatever changes you have done. So you keep hearing about big companies like Netflix and LinkedIn and Amazon of the world running those experiments constantly in production. But it's worth remembering that even those big companies, they didn't start in production on day one. There's a lot of things you can learn by just running those experiments in staging environment. Give yourself a chance to understand the flow of how you plan experiments, how do you execute them, how do you communicate with different people, and how do you get everybody so on board with the whole process of that, hey, one day we're gonna have to run this in production. Are you guys gonna be ready for it? Another thing to consider is that the chaos engineering is not just about stress testing your infrastructure. In fact, we talked to Russ Miles, who's the CEO of Chaos IQ. He talked about how chaos engineering is actually a very good tool for stress testing the entire set of social technical systems that we use to develop software. So the social side of things is probably just as important as the technical side of things. In fact, one of the most important lessons I learned from Russ is that when you approach the business side, the business users, and they're trying to talk about what it is you're doing, don't call it chaos engineering at all. Don't use the word chaos because it's just going to freak people out. Instead, call it what it is, which is continuous resilience testing. And when you frame what it is you're doing in those kind of wording, it makes people a lot more receptive to understanding what your goal is as opposed to just being focused on what it is that you're doing, which is causing chaos. And so for the rest of the talk, I'm going to focus on just the technical side of things, of how do you apply some of these practices to a new paradigm. We talked about the Simian army already. Inside the Simian army, you have the chaos monkey, which kills EC2 instances randomly. You have a latency monkey that can introduce artificial delays, slowness to your APIs. You have chaos gorilla, which can kill an entire AWS availability zone. And finally, you have chaos con that just knocks out an entire region. And then you have also seen a few attempts at basically wrapping the logic of Chaos Monkey into a Lambda function so that you don't have to run a server 24/7, just so that you can use it to kill other servers from time to time. But that's not what I'm interested in. I've been working with serverless technologies such as AWS Lambda in production for a while now. What I'm really interested in is how can we take the existing practices and the principles of chaos engineering and apply to this new serverless paradigm where, remember, there is no server, there is no server that I can physically, that I myself can access, and therefore I can then terminate as part of my experiment. But then again, chaos engineering is not about killing server. Sure, is what most likely what we do when the most likely failure in our system is failed EC2 nodes, failed instances. So in order to stress test our infrastructure against the most likely failure, sure, we will kill EC2 instances as part of our experiment, but the chaos engineering itself is about identifying weaknesses before they actually happen in production in system-wide aberrant behaviors that we just don't control. And we shouldn't confuse the principles or why we do something with the things, the action that we take in order to apply those principles. And having worked on several non-trivial serverless architectures, including with my friend Thomas there, we worked on a social network where we migrated pretty much the entire backend system to run on serverless, to run on Lambda functions. One of the things I learned in the process is that there's just way more inherent chaos and complexity inside a serverless architecture. You end up with many and smaller units of deployment, which is great for many, many reasons. But you also end up with a lot more of them than before, which means now it's harder for you to harden around the boundaries of your services, because there are just way more boundaries now you have to think about. Every single one of those Lambda functions need to be hardened around in terms of how you interact with the other services that you're talking to, in terms of handling failures in your dependencies, your databases, your queues, and so on. And also, as people that are using, as someone who's used to using serverless technologies to build applications, I just want to get away from having to manage servers at all. Even the most important part of my application, the compute layers, I don't want to have to think about servers and manage that for the most important part of my application. Why do I want to run and manage servers for other things that depend on, like databases and queues and so on? So chances are you're going to find guys who are using Lambda to be using also many, many other managed services that AWS and other cloud providers provide. Now, all of these services, all of these intermediate services that you depend on, they all come with their own set of failure modes as well. Excuse me. Some of those failure modes are documented, but I'll bet you that many of them are not documented. Maybe for a simple fact that maybe the owners of those servers don't even know about some of those failure modes that can happen. And even the failure modes that are documented, there's no way for you to really to verify the behaviors of those systems under those failure modes until something actually happens. And then the thing is, we talked about now you have many component deployment units, and for every single one of them, you also have to make sure that you configure them correctly. In the case of Lambda functions, you need to make sure that it's got the correct timeout for the function itself, but also importantly, IAM permissions. You'll be amazed at the amount of times I develop a new feature, I create a new function, and then the first thing that goes wrong is the function doesn't have the right permission to talk to a database, for instance. The fact that now we can provision individual functions with the right permission is great in that we have far more granular control in terms of what our functions can access, so we can be more so from a security point of view, it's a lot better than applying one set of rules, permissions to entire service. Many endpoints, maybe it doesn't have way more permission than it needs, but at the same time, it also means now there's more things that we need to do and more things we need to configure, and there's more opportunity for us to get something wrong in the process. And everything else the platform does for you as well, from scheduling containers to scaling to polling kinesis streams, for example, or to retry fail invocations. All of those capabilities the platform offers also come with their own failure mode. Again, many of them are not documented, and even the ones that are, we don't really have a way to verify them either. So oftentimes in practice, when something does go wrong, for instance, if the layer in AWS that's polling kinesis streams and then calling your function with events, if something goes wrong there, there's no meaningful alternative that I can do in order to mitigate, to defend against that, because the state of the poller themselves are out of my reach. They are part of the black box that I get with the Kinesis and Lambda. That said, there's still plenty of weaknesses in my own code that I can do something about, that I can build defense against. Quite common problem would include my function is not properly tuned in terms of when it talks to downstream systems. So if one of my downstream APIs is responding slowly, then it causes my function to get timed out, or perhaps I'm not handling errors. Well, I've got missing error handler, so that if some downstream system fails, it also takes my service with it as well. Or in the cases where I could have, where say DynamoDB is having a problem, I could have used some fallback value, could be some default value, and maybe I'm missing some of the fallback values. Or in cases where you have to deploy to multiple regions, so you have another way to make your system more resilient by using multiple regions. Maybe you're missing a trick by not having those region failover. And the most common problem I run into in production tend to be performance or latency related, as they can be symptomatic of a whole host of other issues underlying. Could be networking issue in AWS, it could be you're hitting a server that's overloaded, or maybe just unlucky you hit a server that's doing a GC pause. So step 1, we have to decide what steady state looks like for us. In this case, I need to decide what metrics I should use to monitor my system, and what metrics I should use to define my steady state with, and that entirely depends on what kind of system you're building. Common good candidates include the tail latency. Tail latency is like 95 or 99 percentile latency, error count, or probably more appropriate yield and harvest, yield being the percentage of requests that actually complete with, say, 200 or 400, and harvest being how accurate your responses are. This is especially the case if, say, your endpoint returns a list, but if results from very different sources, but if some of the sources are having an outage, then I'll return just the data that I was able to collect. So you will sacrifice the amount of results that we return. And then now the next step will be to then hypothesize how a system will behave. And this is where there's a couple of things we need to consider, because when it comes to building serverless architectures, one thing to keep in mind is when you're building APIs with API Gateway and Lambda, even though a Lambda function can now run for up to 15 minutes, API Gateway has got a hard limit of 29 seconds. So even if your function can run for much longer, API Gateway is going to time out after 29 seconds. And one thing to keep in mind with Lambda is that you've got this process of cold start. When a container is first created, then serve request first time, it's going to take a certain amount of time to bootstrap the container, the runtime for your language before you execute your code. So even if I've got two endpoints, both with API Gateway and Lambda, I know for a fact that that function can only run for, say, 3 seconds because I've set a timeout to 3 seconds. The actual response time I can experience from the calling side can be a lot longer by the time I take into account the cold start time it's going to have. And the rule of thumb in microservices is to use short timeouts whenever you're talking to other APIs. But this is where, the goal of your timeout strategy should be to give your HTTP request the best chance to succeed, but not at the cost of causing your caller to also get timed out. And this is where I find that trying to find the right value is quite tricky. If you make them too short, then you're not really giving those requests the best chance to succeed. At the same time, if you allow those API calls to take too long, then chances are you can then cause your function to be timed out by the Lambda service itself, and therefore that translates into a 500 response back to your caller, and hence causing a cascade failure throughout the whole call chain. And this gets worse when you've got many functions, you've got functions that are making multiple API calls in one invocation. And this could be the case of, say, I've got one API endpoint with a Lambda function that is calling DynamoDB, get some data back, manipulate data, and then save the changes back into DynamoDB before publishing an event into Kinesis. So in that function alone, I've got 3 different API calls. And I see 2 common strategies for people use in terms of deciding what timeout to use for those. One approach is, suppose I've got a function that's got a 6-second timeout configured for the function. And so for each of the API calls I'm making, I'm going to equally divide the 6 seconds so that every single one of the requests gets 2 seconds. In this case, even though overall we have got enough time to make all 3 requests, but the second request took longer than 2 seconds, it was timed out. So in this case, we're not giving all the requests the best chance to succeed. A second approach I often see as well is we are a bit more optimistic in this case. So I've got 6 seconds in invocation time, and every request I'm going to make, I'm going to give you 5 seconds. So in this case, even though none of the requests took longer than 5 seconds, so we didn't time out any of these requests individually, but together they took too long. So before I had a chance to respond to my caller with some data, my function itself, my invocation got timed out by Lambda because it exceeded the 6-second timeout I've configured for the function. So instead, what I propose is, in this case, is we can actually set the timeout we use for those external API calls dynamically based on the amount of actual invocation time we have left, which conveniently we can find from the context object that every single invocation has, where we can find out how much time we have left in the current invocation. In this case, every invocation will reserve some amount of time at the end for recovery, but then every request we make will give as much time as is left in the current invocation minus recovery time, so that in this particular case, we were able to make all 3 requests, even though one of the requests was slow, that's fine. So we are giving all the requests the best chance to succeed. In another case whereby, okay, one of the requests in the end, one of the requests timed out took too long. And in this case, we still have some time at the end right there to do recovery, which could include making sure that you log the timeout incident with as much context as possible, including what API was you trying to call, what sort of timeout value you used, as well as any correlation IDs that you have collected so far, and maybe the request object itself as well. And you also want to record the metrics for those timeout instances. So maybe you say if you're talking to the user API, then you'll be user API.timeout or something as a custom metric. And in cases where you could use the fallback value instead of the actual response, and which is a pattern that actually is baked into the Hystrix library by Netflix, whereby suppose you've got a function or something that needs to get data from DynamoDB, and that request to DynamoDB times out, then we can return a cache value if we have something, so we return a stale value instead. And failing that, we don't have any cache value for that particular request, then we can also just return a default value. And in this case, you're trading off the precision or completeness of your response for higher availability. And that is a great trade-off in many cases. Whenever you go to Netflix homepage, that's exactly what they do. They try to fetch one of your roles based on your watching history and so on. I've got Benji here and Deadpool. Surprisingly enjoyable, Benji. But if that particular service that returns that data is not available, then Netflix will actually return, instead of crashing out the whole lot, it will return the default rail that they show for every new user to Netflix. So being able to use the service with a degraded experience is better than not being able to use the service at all. So whilst that's a good trade-off for many cases, it's probably not the right thing to do for every single case. For example, if someone is trying to go in and check their bank balance, maybe don't return a default value of 0 because that's just going to freak someone out. The next thing you're going to do is to call your customer support and say, what do you do with my money? So the point is that even though trading precision for availability is a good trade-off for many cases, you need to, the most important thing here to consider is still your user experience. And you definitely want to make sure that you give your user the best experience possible. And then that brings us to how do we then inject failures into our serverless application. Consider a simple setup where I've got a client that talks to 2 public-facing APIs and then an internal API that both of those functions talks to. And the hypothesis is that our public-facing APIs is handling slow response from those internal APIs. What we could do in this case to simulate those kind of those failure modes is to we can inject latency into the HTTP client, which I'll show you how you can do that later. But we should also do the same thing for other services that we depend on that we don't own. That could include any number of AWS services that we use. In the case of AWS, we can actually inject latency into the AWS SDK itself as well. Again, I'll show you how you can do that later on. But then, and remember, we have to consider what blast radius are we looking at for this kind of experiment. In this case, because you can't really see color. Okay, so in this case, because we're impacting this particular function, and it's only going to impact the client and the client that's talking to that particular endpoint that's surfaced by that particular Lambda function. So we're not likely, so the blast radius is quite small, so we're not likely to cause any cascade failures in the system. But then if your hypothesis is that, okay, if the internal API is starting to respond slowly, everything else is going to be fine. So you also then want to exercise making sure that everything that depends on that internal API is also handling slow response time properly. So you can also inject latency directly into the function's invocation time itself. But in terms of blast radius now, okay, you can potentially you can inject latency here, but then that is going to impact everything else that talks to that internal API. So your blast radius now is getting quite big, and you can actually cause cascade failures in the system unintentionally. So remember, the point of what we're doing is not to actually hurt production. So we need to make sure that when you're thinking about those kind of experiments, definitely start with in an environment away from production where the stake is not so high. I also find that this type of experiment is actually quite good, even though they can be quite risky at weeding out problems very, very quickly because you are impacting so many things at the same time, and also good in a different way. One of the things I find is, one of the pitfalls I find with software development is that we are not priming developers to think about failures early enough, especially when it comes to greenfield projects whereby you spend months and maybe sometimes years developing against a dev environment where there's minimal load, you almost never see any slow response time or any errors, and the moment you deploy something to production, all hell breaks loose because you've never thought about those kind of things that can go wrong before. And so we're not programming our developers to think about the kind of turbulent conditions that our code is going to find itself in once it goes into production. And in psychology, one technique that we have is called the priming, whereby we can subtly influence the way someone thinks and behaves by repeatedly projecting them to the same set of stimuli. And that is, in fact, what Facebook does when they were trying to enter the Asia market, where network bandwidth is much limited. So on Tuesdays, they got this whole thing called the 2G Tuesdays, whereby on Tuesday they would adjust the bandwidth on the office Wi-Fi to mirror what 2G looks like, so that as a developer working on the Facebook app, I'm constantly reminded of what it looks like, what it feels like to use Facebook for someone who is in Asia, where the network connection is the network bandwidth is much more constrained. And so this kind of experiments, this kind of exploratory experiments that can potentially have a large impact can actually be quite useful in a way to make our dev environments better resemble the turbulent conditions that we should expect our production system to survive in. And Okay, I think I missed a slide here somewhere. For example, if we make, say, in the dev environment, we make 3% of all requests, make them slow or make them return 500, so that if we have a small percentage of requests, always are reminding our client developers that, hey, sometimes that API can fail. I need to think about that. I need to put some error handling around that. And of course, your mobile and web clients is also a very important part of the system. In fact, it's your last line defense before those failures in your system start to impact your user experience. So you should definitely include them in your experiments as well. In this case, we can do the same thing as before, but we inject latency into the functions that are your public-facing APIs. And in this case, the blast radius is still relatively small because it's only between those functions and the client that are talking to those specific endpoints in your API. And equally, we can also inject latency into the HTTP client that the client application is using to talk to your backend services as well. And whilst the experiments are running, we are watching the dashboards, we're looking at the metrics, and when things are finished, when the experiments are finished, then we go back, we dig a bit deeper into other lower level metrics to see whether or not we can find evidence that our steady state was impacted by the experiment. So in terms of how do we actually then go ahead and inject latency, if you're working with a static language like C# or F# or Scala or Java, then the chances are you can use a static weaver like Post# or Aspect-J, which is an approach that I used quite a few years back, whereby to inject small amount of latency and the rate of failure to our system, to our .NET application, we use the Post# to weave those in. For the case of, say, if you're using JavaScript or Node, for example, then you can't really have that because there's no weaver for those. What you can do instead is to manually create the wrapper libraries. As an experiment, I show how you can do this by creating a HTTP client that, in this case, takes in a configuration object that allows me to toggle those experiments on and off, and also control how often we're going to inject latency. And I'm just using Bluebird to add an arbitrary amount of delay to this HTTP request. And as a caller, you just have one method that takes in that part. You pass in some options. In this case, one of those properties on the option object will contain the configuration for those chaos experiments. And ultimately, those configuration comes from, in this case, I put them inside SSM Primary Store, which is another service that Amazon provides. And because I really want to see some latency being injected, I set the probability up to 50%, and I hooked up my service, my API with X-ray, so I can also see a trace of everything that's happening. I spend the time to inject my code. So in this case, I can see no latency was injected, and the HTTP request completed within 60 milliseconds. But on another API, on another request, I can see 3.4 seconds was added to this HTTP request as part of the HTTP client. So that's all well and good for essentially a library, a module with just one method. What do you do with something like the AWS SDK, where it's not feasible for you to create wrappers for every single client library for all the AWS services that you want to use? So what you could do instead is, at least I took a leaf out of Bluebird's promisify or factory function. And in this case, I got a pretty badly named function called injectable OR that takes the AWS SDK client object and override the get, in this case, get async function, and make it take in another object, config object like the one we saw earlier, where I can configure when and how much the latency to inject. And as an experiment, I see that, okay, when I make a request to DynamoDB, in this case, I've injected 1.4 seconds to that request to DynamoDB to simulate what happens when DynamoDB is being slow. All that code is available on GitHub for you to play around with, but we don't have to stop at adding latency to our application layer either. That we can also inject all kind of other types of errors to simulate different type of failures that we're likely to see in production. Some common candidates include just a 500 response from some API that you depend on. Or in the case if you're using AWS services, there's AWS service-specific error cases you should consider. One thing that gets me all the time, and me and my colleagues all the time, is when you're developing against, say, DynamoDB, you're not thinking about a case that, sometimes DynamoDB you can get throttled when the throughput goes over when you put too much traffic, or when your traffic is too spiky. And in the case of Lambda, you also need to think about what happens when your Lambda functions themselves are throttled by Lambda. Because with Lambda, you have a default regional limit of 1,000 concurrent execution at the same time. So when, say, you have a massive spike in traffic and it pushes you over the regional limit, then function is going to get throttled, and you have no control which function gets throttled. So it's important to start to simulate those scenarios and see how it's going to impact your architecture or your system overall. So suppose your hypothesis is that your functions is handling those errors correctly. When you're talking to HTTP response, then again, you can inject HTTP 500 responses to the HTTP client, similar to how we injected latency earlier. And if you're talking to DynamoDB, and the hypothesis is that when DynamoDB starts to degrade and become slow or start to get throttled, we are handling those in a graceful manner, then you can also start to inject those errors into the AWS SDK directly yourself as well. And another interesting case is to run an experiment and see what happens to the rest of your system when, say, a particular function, maybe a critical function in your pipeline is now being throttled by Lambda, because it then to see whether or not it then causes cascade failures in your entire application. You can also, as part of that experiment, and only during that particular experiment, you can also change the reserved concurrency setting for that particular function. Reserved concurrency, I know it sounds like this is my minimum level concurrency. That's not how it works at all. It's a terrible name for a feature. This is basically your maximum concurrency for that particular function. In this case, I'm saying at any moment in time, there should only be one execution of this particular function. So if I want to simulate what happens when I'm trying to invoke this function more often and it's getting throttled, then this is how I can start to simulate those scenarios. The takeaway message I want to give you is that the failures are inevitable regardless whether or not your code runs in EC2, runs in the containers, or runs inside a Lambda function. And the only way for you to really know your system is resilient against different failure modes is to put it to the test. And you do that through experiments that are designed to stress your system against different failure modes so that you can then find out its weaknesses before they actually happen, so that you have a chance to improve the resilience over time. And what you shouldn't do is go straight to production like a happy chaos. Well, I don't know. Go straight to production and then break things unintentionally. Because once you've done that, no business user in the world is going to let you go anywhere near production with your fancy chaos experiments ever again. So definitely do not do that. And with serverless technologies like AWS Lambda, there are way more inherent chaos and complexity in the system. And if anything, there's even more need than ever before to really find those weaknesses early using chaos experiments so that we can start to vaccinate our serverless application against failures nice and early. So with that, thank you guys very much for your time. And if you want to learn a bit more about how to make your serverless applications production ready, I also have a video course with Manning as well, which for now you can still get 40% off with that code on the screen. So yeah, thank you guys very much. Do we have time for questions? Okay. One sneaky question you've got. Cool. This question there.
Have you experimented with introducing latency based on statistics of previous calls? So say you know that 95% of your calls complete within some time frame, and you use that as the timeout.
I haven't. So the question was, have you thought about using heuristics from previous and to decide how much latency to actually add? No, I haven't. So right now, so far as my experiment goes, is just, hey, here's a number that's definitely going to make my function timeout. So let's see what happens when I check that number at my HTTP request, and to make sure that my function is actually is timing out the request itself before the invocation times out.